All right, let's just kind of summarize some things about the alternating series, specifically the alternating series test here. So you want to perform that limit test first. And remember that our terms need to be approaching 0 without the little alternator on it. And I do that part first because if it fails, if it doesn't equal 0, then I'm going to switch to just the actual nth term test for divergence and show that that series actually diverges. And it will diverge because your limit won't be equal to 0 when we put the alternator in there. It's going to go plus minus, plus minus, plus minus, plus minus to some particular number, which is not 0. So therefore it diverges. Okay? And then you check your inequality to see if your terms are actually decreasing. You can do that algebraically by showing that the n plus 1th term is smaller than the nth term. Or sometimes it's easier just to use calculus. You assign a function to it, f of x, for your a sub nth term for n equals 1, 2, 3, and so on, and you find the first derivative. Show that the first derivative is negative. And I do believe that we did that on the integral test, right? So sometimes it's far, far easier to do that derivative test to show that they're decreasing than to show that the inequality is true. And we're going to see that on our next example, I think. Okay. And then that other tip here is, hey, you can't use the alternating series test to show divergence, only convergence. That's all it does. So example 3, determine whether the series summation from n equals 1 to infinity, negative 1 to the n plus 1th power times n squared over n cubed plus 1 either converges or diverges. On this example 3. All right, let's see. Well, it is alternating. I see an alternator right in here, right? And notice that that's definitely not geometric, this thing. So I have to use the alternating series test. And my nth term is equal to n squared over n cubed plus 1. And bear in mind that n starts at 1 and just gets bigger. So this is definitely positive, checks. All right, so now let's take the limit part. First part of our test, the limit, as n goes to infinity, of n squared over n cubed plus 1. If I were to stick in infinity, I'd have infinity over infinity, which is L'Hopitalable. So we use L'Hopital's rule. Now, of course, we could use a little pre-cal shortcut, but what I'm going to do here is I'm going to just be thorough. I'm going to go, hey, now consider the limit as n goes to infinity of, take the derivatives of this, I would have 2n over 3n squared. And then I can cancel stuff, like this n and one of these n's. The limit as n goes to infinity of just 2 over 3n, which, yeah, it's pretty much 0. Man, that was a lot of unnecessary work. I could have just gone, yeah, it's equal to 0 because the exponent on the bottom is bigger than the exponent on the top. The bottom is growing faster, right? I could have done that. Why didn't I? Who knows? I just wanted to make the video longer because that's what I do. All right, let's look at the second part. So the second part, what I'm supposed to do is show that the terms are decreasing. I want to show that the n plus 1th term is less than or equal to the nth term. So for us, that would be n plus 1 squared over n plus 1 cubed plus 1 is less than or equal to n squared over n cubed plus 1. Yeah, so can you see by this one that this is definitely one that we would want to use calculus for? No, thank you. It might be easier just to take a derivative. So I'm going to say let f of x equal x squared over x cubed plus 1 equal n squared over n cubed plus 1 for n equals 1, 2, 3, and so on, right? And then I want to take its derivative using good old-fashioned quotient rule. I would have derivative up top is 2x times the bottom, x cubed plus 1, minus the top, x squared, times the derivative of the bottom, 3x squared, and that's it, over the bottom squared. That's better. Okay, and then clean this thing up. Distribute here to have a 2x to the fourth plus 2x minus 3x to the fourth. Okay, and let's see, combining some like terms, looks like we have a negative x to the fourth plus 2x, x cubed plus 1 squared still. And maybe one more thing, let's pull out, let's pull out a negative x cubed plus 2. All right, so this is going to be kind of like the first derivative test, except for just testing for increasing and decreasing part of this. We have critical numbers. Top and bottom is equal to 0. Well, the bottom, let's see, the bottom here would be equal to 0 at, let's see, x cubed plus 1 is equal to 0. X cubed is equal to a negative 1, so x is equal to negative 1. That's not going to be helpful because we're starting at 1. All right, so it's just the top then. So on the top, we would have x is equal to 0. Why am I writing them over there? I don't know. X equals 0. And for the second one here, I'd have x cubed plus 2 equals 0. Is it a plus 2? Ah, dang it. I didn't factor out the positives or the negative sign there. That should actually be minus. That's minus. Which means I'd add the 2 over, take the cube root. Oh, it's the cube root of 2, not the cube root of negative 2. Yeah, so we have 2 critical numbers. Let's make ourselves a little chart for this. Some intervals. And sure, we're starting at 0, even though it doesn't really start at 0. It starts at 1, whatever, just for the purposes of this function. And then we're going to go up to the cube root of 2. And then the cube root of 2 up to infinity. We want to choose some x values. Cube root of 2. Anybody got any clues how big that is? I don't know. I think I might need a calculator in here. Hey, ignore all of this business. I'm sure that this is stuff that we're going to do here soon. What did I want? I wanted the cube root of 2, which is approximately 1.259, so about 1.3. All right, so that means that picking an x value of 1 is perfectly okay, and then over here, picking an x value of 2 is perfectly okay. These go into the first derivative. All right, so plugging into the first derivative, if I were to stick in 1, ignore the bottom because it's always positive. If I stick a 1 up top, that'd be a negative 1, and on the inside, it'd be a negative 1 minus 2, which is also negative. Negative times negative is a positive, which means f is increasing. Ooh, that's kind of a problem, isn't it? Not really, because whenever I stick in 2, on the outside I'd have a negative 2. On the inside, 2 cubed is 8. 8 minus 2 is positive, so the whole thing is negative, and then it starts decreasing from there on after. So it's not like its first term. For the first term it goes up, and then it goes down for the rest of them, and that's okay. So we're going to say that since f prime of x is less than 0 for, let's see, x is greater than the cube root of 2, then f of x is decreasing on x is greater than or equal to, increasing, decreasing happens on closed, cube root of 2. And what that means, this implies that a sub n plus 1 is less than or equal to a sub n for So everything bigger than, well, it's not the first term because the first term over here, it increases. I don't want that one. So it's past 2 for x greater than or equal to 2. There we go. So that satisfies both conditions, right? So remember back up here, we showed that the limit approach 0. So the terms are approaching 0, individual terms, and they're decreasing towards 0. Therefore, our series, sum from n equals 1 to infinity, negative 1 to the something, I don't even remember, n plus 1? Yeah. N squared over n cubed plus 1 converges by the alternating series test. All right, and there you have it. There is the first objective, basically, which is about applying the alternating series test. What we want to be able to do is show that the limit of the terms are approaching 0 without the alternator, and then show that the terms are also decreasing, and that's enough to show that an alternating series actually converges. In the next lesson, or the next video for this lesson, we'll talk about like approximating the sum of an alternating series and see how far off we can be with the alternating series error bound.